So today we're going to finish the whole chapter 6. The first topic we will to talk is just what is the central limit theory. So in this section 6.4 we will talk about what is the theorem, and we also will talk about some important applications about the theorem. So first let's check what is the central limit theorem. We have lots of samples. So for all samples, and we should know the sample size of each sample. Sample size and for each sample should be greater than 30. Then we can talk about the distribution of the sample means. So remember, each sample we can get the sample mean. And we will talk about the distribution of all the means, all the x bars. Then we will say the x bars can be approximated by a normal distribution. This time we are not talking about the single x value anymore. We are talking about the distribution of all the x bars. But this time we have a normal distribution, right? All the x bars approximately follow a normal distribution. The mean of this distribution is mu, but the standard deviation is a special one. The standard deviation, you should be really careful about the standard deviation for the means, not for the x. So it's not the same one. So let's check the condition, right? The population with any distribution. So it can be binomial distribution, it can be uniform distribution, any distribution, but has the mean equal to mu and the standard deviation sigma. It's not necessary to be normal distribution for the population. The population can be any distribution, not necessary to be normal distribution, but has the mean is equal to mu and the standard deviation is sigma. And we know the samples with the same size n, all the samples, same population, same size. So all the samples should be selected from the same population with the same size n. Again, same size, same population for all the samples. So the requirements here is we have two kind of requirements. The first one is population. If the population, remember we talked about the population can be any distribution, but if it's the normal distribution, then we can use central limit theory. We could use central limit theory. Or if the population is not a normal distribution, or we will say we do not know what kind of distribution it is, but we know the sample size is greater than 30. The sample size is greater than 30, then we can still use the central limit theory. So either condition is qualified, then we can continue to use central limit theory. It's not necessary to qualify both of them. It's not necessary two of them to be satisfied at the same time. Only one is enough. If the population is normal distribution, then any sample size will be okay to use the central limit theory. Even the sample size is very small, something like 5. But we already know the original population follow normal distribution. Then we are free to use central limit theorem. Another situation is we do not know the distribution of population. Or we already know the distribution of population is not a normal distribution. It's not a normal distribution. Maybe it's just a binomial. But we have the sample size greater than 30. We could still use the central limit theorem. So that's the requirement for using the central limit theorem. Let's see if we use the central limit theorem. So the formula is not shown correctly. So make sure you check my handwriting. Here, the mean of all the x bars, or we will say the mean of all the sample means, is just the population mean. So the mu is just the population mean. Another rule is here. This one should be the sigma. So that's the standard deviation of this x bar is the population standard deviation. This time not the same one. We have a denominator to get this one. So if you check your PowerPoint, I think everything looks all right, but I do not know in my screen it's not the same one. So make sure you check this one. Again, mu of x bar. So that means the mean of all the sample means is just equal to the population mean. But the standard deviation for all the x bars is not equal to the sigma. It's not equal to the population standard deviation. It has the square root of n as the denominator. So we will have another formula for z-score. But this z-score is not for single x value. It's just for a sample mean x bar. So here, the numerator will be x bar. The first term this time is not the single x value. It's the single sample mean. We have lots of sample mean, right? We have lots of sample. We will have lots of sample means. We are talking about the distribution of all the sample means. So here, this is the single value of sample mean x bar minus the mu value. That's the population mean. That's the population mean. Because it's just the mean value of all the sample means. So this x bar is the single x value. This is the mean of all the x bars. And the denominator should be the sigma divided by square root of n. Because this whole part is the standard deviation of the x bar. So make sure you know there's a big difference between two kinds of z formulas. If we are talking about the single x value, then the denominator will be just sigma. If we are talking about the single x bar value, we want to get the z-score for single sample mean, then the denominator will be the population standard deviation sigma divided by the square root of n. So that's the C formula for central limit theorem. Central limit theorem is just talking about the distribution of all the sample mean x bar. Not the single x value. So let's check this one again. If the population is not normally distribute, and the n is not greater than 30, so it's less than or equal to 30. So do not, the method, so the central limit theory, do not apply it. Of course, each time you have a problem, you need to check the requirement. So again, if the original population, we know it's a normal distribution, then you do not need to check the sample size, because this one is already enough to use the central limit theory, the normal distribution. But sometimes, most of times, we cannot know the distribution of original population, so we need to check the sample size. So if sample size is greater than 30, then any population will be fine. If the original population follows a normal distribution, then any sample size will be fine to use the central limit theory. Okay, the second important point is we are working on the individual x value or the mean value from the sample. So this means we are working on x, and this means we are working on x bar. So if it's a single x value, so this is not about the central limit theory again. So you need to use the original z formula to get the z-score. But if you are talking about the mean value, you are talking about the x bar, then it is about the central limit theory, which means we should pick the special z formula just for central limit theory. The difference, remember, the denominator is a different one. Sigma divided by square root of n. So again, it is the formula this is for individual value. For x, make sure you know this is x. The single x value, the single value of x. But if we are talking about x bar, then the formula is not the same. This one is, make sure don't forget the square root of n term. And we also call that term standard error. We have a special name for this standard deviation. We call it a standard error. Okay, let me change it. So this is sigma. This is mu. And this is mu. So sigma. So just like I said, we call it standard error. The standard error means the population standard deviation divided by square root of n. This is also the standard deviation for x bar, the sample means. Again, the standard deviation for the x bar is not. So this one is called the standard deviation for all the x. This is called the standard deviation for x bar. So we give it a new name called standard error. Let's check the example. Okay. So in this example, we have this rule, 4,000 pounds, 27 passengers. So if the capacity is 4,000 pounds, 27 passengers, we can get the mean passenger weight for this case, right? Total 4,000 divided by 27 passengers. So we can get the mean weight of the passenger is 148 pounds. So how can we get this? Total 4,000 pounds divided by 27 passengers. So the mean weight for each passenger is 148. We assume a worst case scenario. 4 with 27 adult males. So the adult males have weights that normally distribute. Very good. We have this word. We know adult males, the weights of adult males are normally distributed. And with the mean, so here we can write this. Mean is 189 and the standard deviation, so we have this one. This is for the weights of adult males. So this is our mu and this is our sigma. That's the basic information from the question. Let's check. Find the probability that one randomly selected adult, so one randomly selected adult male has a weight greater than 148. And we have another question, part B. Find the probability that a sample of, this is talking about a sample of 27 selected adult males has a mean weight greater than 148. So the first part, the value is greater than 148. The second part, the value is also greater than 148. But what's the difference between part A and part B? So we will check it later. So basically, I will transfer this to the symbol. One adult male has a weight, so it's just the single x value, single weight. So it's the x. And the second part, a mean weight. So it's not called a single x value. The mean, this is the key word here. The mean weight, we should use x bar to represent the mean weight. Let's check the solution part. So let's check the question A. So first we need to get the probability, right? But for any continuous distribution, we know we can use the area under the density curve to get the probability. So how can we use the area to get the probability? We need to use a table, remember? We should use the C table. But here, can we directly use the C table? Do we have the Z score already? No, because we know it's a normal distribution. But the mean is not 0. The standard deviation not 1. So this is just the general normal distribution. It's not the standard one. But it's not too difficult to transfer this general standard deviation, a general normal distribution to a standard normal distribution. We only need to get the Z-score, right? Do the Z transformation. But from the question A, we already know it's an individual value because we are talking about X. X, the value of X is 148, but we know we want to get the area. X is greater than 148. Remember? Here, greater than, so we write here, greater than. If we write down the greater than sign, we should remind ourselves we are actually interested in the area cumulative to the right. We are talking about the area cumulative to the right side. So we sketch a curve. Write down the value x we have, and we also put the mean in the middle. Then we shaded the area we are interested. Then the step 2, we do the z transformation conversion. Okay, so here it's the single x value. So you realize then the denominator will be the simple one. It's just the sigma. So we plug into the value. Remember, the first value will be 148. It's the single value we have, x, minus the mu. The mu, we get it from the problem. It's 189 divided by the standard deviation. We will get a negative. So it's possible to get a negative sign, a negative z-score. Because you see, the mean is right in the middle, and our x value here is smaller than the mu, smaller than the mean. Then the z-score will be a negative number. So after we get a negative z-score, next step, we should check our z-table, right? If you have the table with me, we can check the negative z-table. And we check negative 1.0 in our left column. Then we check the last digit, 0.05 in the top row. We will locate the body of the table. This body of the table, this value in the body of the table, 0.1469, is our probability. But is that the final answer we get? No, we will say no. Because from the table, you will get the area. But this area is cumulative from left. Is cumulative to the left. Because the z-table only gives you the area cumulative from left. But in this case, remember, we are talking about greater than 148, which means we are actually interested in the area to the right. How can we get the area of this green shaded part? We use the total area, because we know the total area under the curve is 1. So 1 minus the area cumulative to the left. We can easily get the area to the right. This step is not hard, but sometimes you will just forget this step. Make sure don't mess up the left side and the right side. So this case, 0.9531 is the answer for part A. But we still have part B, right? Part B is talking about the is no longer talking about the single x value. We are actually talking about the mean value, the sample mean value. If we want to test a sample mean, we want to get any conclusion about a sample mean, which means we should use the central limit theory. But if we want to use central limit theory, we always need to test the requirements. So here we quickly test the requirements, because from the original description of the problem, we know the original population, the weight of adult male follows a normal distribution. Remember the requirement of central limit theory. If the population is a normal distribution, then any size will be okay. We are free to use central limit theory. So here is the case. The sample size is not so important for this case because the original population already follows a normal distribution. So we test we could use the central limit theory for the part B. And we can list the parameter for this x bars. So mu x bar is just equal to the population. But the sigma of x bar is not the single sigma. It should be divided by square root of n. So we could go back to check, how can we get this? This is the mu, right? The original population followed the normal distribution with a mean equal to 189, and with the standard deviation 39. So standard deviation here is 39. But where can we get the sample size n? We go back to check it. Here, from part B, we know if we select a sample of 27. So sample of 27 means the sample size is 27. So that's how we get the n value. After that, we get this mu standard deviation or standard error for the distribution of x bar. So this is the shape. This is normal curve for x bar. It's not for the original x, right? We can use this distribution to get the answer of second part. So here it's the x bar. We are talking about the x bar. So this part we can write like this. So we plug it into the values. This time we know the mean value is 148. So the mean value, the single mean value, the sample mean value is the first term, minus the population mean or the mean of the sample means, mu sub x bar. So this is just equal to the population mean. So we just use 189. But make sure, don't forget the square root of n for the denominator part. This time we have negative 5.46. So we have another z-score. This z-score is from the x bar, it's not from x. But we still do the same thing, right? If we check the z table, we check the negative z table, and we know from this z, we check the table, we will get a very small probability, very small area. But this one is still not the final answer because we are talking about x bar greater than 148. It's still about the area cumulative to the right. So we use total area minus the area cumulative to the left to get the area cumulative to the right. So this 0.9999 is the answer of part B. Make sure you know the difference between part A and part B. Again, part A is about single x value, single weight in this case. And part B is about the x bar, the sample mean. So in this case, it's just the mean weight. The key word is mean. If we are talking about mean, we are actually talking about the x bar. If we're talking x bar, we actually want to use the central limit theorem. So this is the interpretation. Let's see. The probability of single male more than 148 pounds is 85%. But randomly select 27 males. The mean weight of this 27 males is greater than 148 pounds. The probability of that situation is really high. So almost, it's certain to happen, this case. So we will say it is almost certain it will overweight if randomly selected 27 adult males. So that's the worst case. It's almost certain it will be overweight because the probability 0.99998 is very close to 1. It's certain to happen. And we talk about the rare event again. This is the third time we're talking about this rare event rule. So we have assumption. We have an assumption. And the probability with that assumption is very small. Very small. The probability here is very small. How small? Maybe we will say it's less than or equal to 0.05%. Less than 5%. Then we conclude the assumption is not correct. It's not correct. Let's check the body temperature example.